I didn't get a chance to write anything on the board, so you just have the announcement for something that passed already. But I will be writing a homework assignment over the math that we're going to be doing today. Won't be due until next week, so you'll have some time to work on it. And then I will also be posting a prepare to learn for the end of chapter 12. So I want to finish up chapter 12 next week. After that, we just have 2.5 weeks left of classes. So getting close to the end of the semester. But in that 2.5 weeks, we have to learn about equilibrium and learn about acids and bases. So we've got a lot of material to get through. So there are going to be some things that I'm going to leave out. And if you are just taking this class as a requirement for this is your last chemistry requirement for whatever thing you're going to be going into, probably not real important, the things that I'm leaving out. If you are taking this class because you are going on in chemistry and because you want to be a doctor or a pharmacist or a veterinarian or things like that, you may have an exam like the GRE or the MCAT or the PCAT or something that's going to ask you some of the questions that I'm just going to barely touch on. So you may want to read the last few sections of the chapter a little bit more carefully and try out some of the sample problems in there just to make sure that you've at least seen that kind of thing before. So that's kind of where we are going. Okay, so this is section 4 of chapter 12, integrated rate laws. So integration is in reference to calculus. And so I mentioned some calculus on Monday. And so that's just how we get to these rate laws, these equations that we're going to be using. So the important thing isn't really how we get there, it's just what the equation is. But integration is how we get there, if that's the kind of thing you care about. Okay, so what I want to look at here is some graphs of concentration changing over time. Now, these are two reactants in a chemical reaction. And as reactants, we expect their concentrations to go down over time, right? Because we're using them up. So that's no surprise. Now, most of the graphs of concentration versus time that we looked at the beginning of this chapter look kind of like the bottom here, it was curved, okay? But in this case, we've got one that's a straight line. So if we think about why would it be curved, it's because the concentration affects the rate. That's what we said of the 4 things that can affect rate. Concentration was the one that we were focusing on for the first half of the chapter. Okay, so since I'm lowering my concentration, the rate slows down. And so this becomes less and less and less steep, and that's why it's a curved line. But the straight line is showing that for W, and that is tungsten. So as tungsten decreases its concentration, does the slope change? No, the slope is the same the whole way. That's kind of the whole thing of a straight line, is it has the same slope the whole way. If the slope isn't changing, what does that say about the rate? The rate doesn't change. So slope doesn't change, rate doesn't change. So straight line means the rate isn't changing. And then if we think back to those charts that we had where we were comparing different reactions, when we saw a rate didn't change, what did that tell us about the chemical? It was zero order, right? So we can look at this graph and know that if we actually have a straight line, that this reaction is zero order with respect to tungsten, okay? So what does a straight line mean? It means, first of all, that the rate isn't changing. And the implication of the rate not changing is that the reaction is zero order with respect to that chemical. So remember, each chemical has its own order. So if I were to look at the rate law for this equation, this wouldn't appear in there because the concentration of tungsten raised to the 0 power would just be 1. Okay? This one is going to have some dependence. Now, for that bottom one, which you might not be able to see, it's silicon dioxide. For the bottom one, can I tell if it's first order or second order? No. If you have a really good eye, you might be able to figure it out, but just seeing that it's curved doesn't really tell us anything. So what the integrated rate laws are going to allow us to do is to determine whether something is zero, first, or second order. Okay? Next week in lab, you're going to collect data and plot it. And then as you plot it, you're going to look, is it a straight line or is it a curved line? And if it's a straight line, you're going to know that it's zero order. If it's a curved line, then we have some other tests that you can do, and they're related to these integrated rate laws. Okay. So for zero order reactions, remembering that it's zero order with respect to a particular chemical, the rate does not depend on the concentration of that chemical. Now, our rate expression, how we describe a rate, is the negative change in concentration of A over the change in time. So remember that triangle means change. So this first part here is just telling us that's how we measure rate. Okay? The rate law is going to look like this. Rate is equal to K. Okay, so what I did is I put those two expressions for rate equal to one another. Rate is the negative change in concentration over change in time, and that is equal to the rate law, which is rate is equal to K. And we know for a straight line that the slope is constant. And so in a graph of the concentration versus time, which is all the graphs that we've looked at so far, concentration versus time, we will see a straight line. Now, I'm sure in algebra classes, you spend a lot of time with different equations that represent straight lines and have seen the equation y equals mx plus b several times. That looks familiar to you all? Okay. So what is m in the expression y equals mx plus b? What does that represent about the line? The slope. Okay. And what is b? The y-intercept. All right. So in this equation, we've got it kind of reversed. The mx is at the end and the b is at the beginning. And we do that because we've got a negative in front of it. But x is our time, so t here is time. And the thing that we multiply by x is our slope, right, mx. So the thing that we multiply by t is k. And what is k? That's our rate constant, right? So if I had the equation for the line, I could just look at the slope and know what k is. Now, in kinetics, most things are going to be positive, right? And that's true with your rate constant as well. But we know that this is a downhill line, and a downhill line has a negative slope. So we have negative k here, which means that our slope is going to be a negative number, and we'll drop the negative to get to the k. All right, and then our intercept then is going to be what? Y-intercept is going to be the initial concentration. So y-intercept is this A with a 0 next to it, and that means the initial concentration. So that's the concentration that was on the bottle before you mixed your two chemicals together. I've circled this here because as we look at other graphs today, time is always going to be on the bottom, but the y-axis is going to change. So what we need to be paying attention to, and in lab next week, you're going to need to be paying attention to what is on that y-axis. Okay, so that's zero order reactions. Don't always have zero order reactions. There we go. Okay, so we've already said this. As the reaction progresses, the concentrations of the reactants and the products change. The reactants go down, the products go up. And so this is some example data. So here we have time and the concentration for each of these things, and that's what's plotted up here. So we just have concentration, you have the square brackets around the chemical. And then we have some other things calculated here. They're going to show up in a little bit on other things. As we look at this, one of the things that we looked at with the graph is calculating the average rate. And so we said we could look at the average rate by looking at this line, right? From the beginning to the end. Was that a good approximation for the rate at any given time? Not really, because our rate is constantly changing. And so at the beginning, it's a lot more, and at the end, it's a lot less. Okay, so what we're going to look at here, because this isn't zero order, it's not a straight line, we're looking specifically at a first order reaction. And what is graphed is the change in the concentration over time. So the top part here, this rate here, is what the slope is. And then our expression for what's going on here is going to be a little bit different. But we know that those are two ways we can say rate. All right, so if we wanted a better approximation, and we're often interested in the initial concentration, right? But we might be interested in the initial or the initial rate. We might be interested in the initial rate, or we might be interested in the rate at a different time. But let's look at the initial rate first. A better approximation might be this one, right? That's closer to what the slope looks like. So we made our interval smaller. If I make it even smaller, we get a pretty good approximation, right, of that initial rate. Now, depending on how curved it is, that, you know, might be just fine, or it might be still a little bit off. And so what we do is we have a method where we look at smaller and smaller and smaller intervals. And that's exactly what calculus does. Okay, so if you haven't had calculus, the idea behind calculus is I can get a better approximation if I take a smaller interval. What happens if that interval gets so small it's infinitesimal? Okay, so that's just the kind of the basics behind where this is coming from. So let me go back here for just a second. I'm going to take these two expressions for rate. Rate is equal to change in A over change in time, and rate is equal to KA, because that's the rate law. And change this up here. This is now rate is equal to KA. And I'm going to set them equal to one another. Okay, so that's all I did there. Then math. Okay, so if you're interested in the calculus, this slideshow is available on Canvas and you can look at it, but a bunch of math happens. Okay, so there's some calculus going on here. We do our integration, we figure out what the expression looks like over a certain time interval. We remember that subtracting logarithms is the same as taking the quotient. And we end up with these two equations. So the blue part is the important part. All the rest is just then math occurs. Okay. So this is the equation that falls out of this up here. So we have this minus this, and we just move this over to the other side. So this is our normal equation. But one of the special rules about logs, and we don't work with logs very often, so you may or may not remember that this happens, but I'm telling you again, is that if I'm subtracting two logs, so I'm subtracting these two things, that's the same thing as taking the log of the numbers divided by each other. So not taking the logs divided by each other, but the individual numbers. So if I have parentheses. Okay? So those are two ways to express the same thing. Why do we care if there's two equations? Well, it depends on what we're trying to solve for. If I'm trying to solve for what the concentration is at a particular time, I want to get the concentration at that time by itself as much as possible. So the bottom equation is better. If I'm trying to solve for how much time has passed, then I might want the t as much by itself as possible. So this equation might be a little bit easier to work with. Or if I'm trying to solve for k, this might be easier. All right, are we good on writing down the equations? Okay, so we kind of did this treatment for the zero order. We're looking at our rate law, our integrated rate law, and it kind of looks like a straight line equation. So it's y equals mx plus b. Now this is a little bit different because y, instead of being just a variable, is going to be the natural log of the variable. Okay. X is still time. Okay. So this is what each of the things in here are. And so notice with this graph, I still have time on the bottom, but my y-axis is different. So if I want to see if it is a first order reaction, I have to take all of those concentration data points and find the natural log of each of them. And as I find the natural log of each of them and graph them, if I get a straight line for the natural log of those data points, then I know it's first order. What is the slope equal to on this? The slope is m. What is m? It's written on the graph. Negative k, right? And k is the rate constant. It's the same rate constant as this k right here. But because it's a downhill graph, it's negative k. Okay, so it'll be a negative number in the equation, but it's always positive. You just drop that negative. Okay, so in your lab, you're going to be asked, what is the value of k? Okay, and the value of k, you're just going to look at that equation for the straight line. And if it's the zero order or the first order, it'll be negative. And so you have to drop off the negative. All right, anything else on here? No. Okay. Anybody still need this slide? Okay, so the next slide just kind of summarizes the things that we've looked at. So this was the same data table I was pointing out before. The yellow is the concentration. So the graph right above it is concentration versus time, typical graph that we've looked at, and we saw a curved line. That curved line tells us it's not zero order. So we're going to test. Is it first order? The way we test is we take each of these data points and take the natural log of them. So we plug in natural log of 0.0165. You get this one all the way down. And we keep those data points and plot them. Now, when you take the log of a number that is less than 1, and usually our concentrations are like 0.1 or 0.05, they're pretty small, you're going to get a negative number. So when you do your lab, if you're plugging in the concentrations, you would have negative numbers. Now, we're not going to use the actual concentrations. We're going to use the intensity of color, because we saw with our copper lab where we had the dark blue copper and then we diluted it and diluted it and diluted it, that the darker the color, the more concentrated it was. So we're going to have the absorption, which is going to tell us how dark the color is, versus time. So it's not actually going to be the concentration, but it's going to be a good approximation of concentration. Okay. So that's what those two are. And then this one circled in red because this is a straight line, and that tells us, yes, this is first order. All right. Now we have to think about second order, and we're going to end up doing that third graph there. So we're going to see what that looks like. So we know for a second order, our rate law is K times A squared. Right, and we're going to do the same treatment that we had before. Take our rate is the negative delta A over delta T. Delta is the triangle. And what does triangle mean? change. Okay, so negative change in concentration over change in time is equal to, make it equal to this rate constant, K times A squared. Right now here I've written K times A squared, over there I've written A squared times K, but that's okay. Multiplication is commutative. It doesn't matter which order you do it in, we've got the same number, so we can switch them around. So we set those equal to each other, and then we math. And after all the math, we end up with the blue equation at the bottom. So that's the important equation, is the blue one. 1 over A, and then we have a little t. So that little t tells us at time t, after a certain amount of time has passed, is equal to kt plus 1 over A at time 0. Remember, A at time 0 is the initial concentration. So this also has the form of y equals mx plus b, but in this case, we have the kt first. And that's because there's something a little bit different about our slope. What is it? It's positive. We have a positive slope here. We don't have a negative in front of that k. And so we end up with an uphill graph. All right, so when we test for second order, and usually by the time you've tested for 0 order and first order, if it's not one of those two, it's going to be second order. Then we're going to have 1 over the concentration and time on the bottom. That didn't change. And it's going to be an uphill graph. And then whatever the slope is, that's equal to K. We don't have to change the sign of it or anything. All right, now this one can give us some kind of funky numbers too, because our concentrations, remember, tend to be pretty small numbers. So if I take 1 over 1/10, the reciprocal of 1/10, I would get 10, right? 10 and 1/10 are reciprocals of one another. So that'd be 0.1. But if I had 0.001, not an unreasonable concentration, that would be 1,000. 1 over that would be 1,000. And normally we're working with smaller numbers there. We're working with 1 to 10 numbers rather than 1,000 or 10,000. So if you have a second order equation, you're going to end up with these really big numbers that you're subtracting from one another. Don't panic. It's unusual, but it just happens with second order. Okay. We good with this slide? Yes.
So do you just have to like recognize the graph and then that's how you apply whichever right law?
So there are 2 ways that we can look at this. One way is that you might be given a graph or a series of graphs and say, what is the order of the reaction? So if you're given 3 of them, look for the one that's the straight line. If you're given 1 and it is a straight line, you're going to look at the y-axis and say, what is giving me the straight line? Is it the concentration, in which case it's 0? Is it the natural log of the concentration, in which case it's first order? Or is it 1 over the concentration, in which case it's second order? Okay. The other way that we might use this is we might say, I want to know what the concentration is after 10 minutes have passed or after 3 years have passed or whatever. In which case I'm going to use the equations, not the graphs, and I'm going to plug some numbers in. And that's what we're going to look at here in just a second. All right, so summary slide here. If it is 0 order, now this can't be the same reactant for all 3 of these, because a reactant is either first order or second order or 0 order. It's not going to be all 3, okay? If it is 0 order, and the order on the graph here, I don't know why they did it this way, the 0 order is the last one, then the straight line graph is going to be our basic concentration versus time. Okay, so if I'm given one graph and it's concentration versus time, and it's a straight line, that tells me it's 0 order. If I'm given one graph and it's natural log versus time, that's this over here. Natural log versus time, being a straight line tells me it's first order. And if I'm given 1 over A, and that's the straight line, that tells me it's second. And then there's the equations underneath each of those. And again, this might be a good one if you go to Canvas and have the slide, if you wanted to print out a slide, this is a nice summary slide, or copy it over in your notes or whatever. Very good summary. All right, can I move on? Okay. Dang it, I thought I had this fixed. Apparently I didn't. Okay. This was supposed to pop up a little at a time instead of the whole thing. Okay, so we're going to do some equations and we have to undo some operations. Now we know that if we're multiplying, so if we had 3x and we wanted to solve for x, that's pretty easy. We're just going to divide by 3, right? No problem. What if we had 1 over x? Okay, so this one's a little bit trickier. If I have 1 over x is equal to 0.25, I need to take the reciprocal to get to x, right? And the reciprocal is 1 divided by that thing. So I can plug into my calculator 1 divided by 0.25. I could also plug into my calculator 0.25 raised to the power of -1. So the power of -1 means the reciprocal. On calculators, you will often see a button that looks like this. Sometimes it's 1 over x, in which case it's more obvious. But if you see this, that's going to automatically take the reciprocal for you. All right, so anybody know what the reciprocal of 0.25 is? So you can probably do this in your head if we think about what's the connection between decimals and fractions. So what fraction is equal to 0.25? 1/4. So if I have the fraction 1 over 4, what's the reciprocal? 4 over 1 or 4, okay? So something like that, you technically could do in your head. You probably want to plug it into your calculator just to be sure, but you know, that's reciprocal. Okay, so the tricky one is the last one, the natural logs. If I have the natural log equal to something, and notice it's negative here because we're going to see a lot of negatives for our first order reactions. The opposite of that is e to them. So a natural log is kind of like a log base 10, but the base isn't 10, it's e. And e is this weird number that has magic properties in it. So on your calculator, you would find that e, and it has to be a lowercase e. So graphing calculators often have a capital E. If you're going to do scientific notation, look for the lowercase e. And then you're going to plug that e in and then plug your number. So e to the negative 0.074. If you're not using a graphing calculator, it might look more like this. You might have e with a caret and these things. Now, these scientific but not graphing calculators usually do a weird thing with logs and with negatives. They reverse themselves. So if I wanted to plug in negative 0.074, I would first plug in the 0.074 and then hit the button that has the plus and minus. That's what makes it negative. If I wanted to take the natural log of it, I wanted to take natural log of, say, 0.25, then I would have 0.25 and then hit the natural log button. So it reverses itself. Okay, now if you have a graphing calculator, it tends to go in the same order that you write it down, so it's not too confusing. You will notice on your calculator, these two are on the same button. So usually natural log is the main button, and then e to the x is the thing that's written above it that you get to when you hit the shift. Okay, and that's because one undoes the other. All right, are we good with the slide, or do we need to stay here? Okay. So now we're going to do an example problem. So the sheet that I handed out is what you want to be looking at. And the first thing you need to do when you have an integrated rate law problem is you need to decide what the order of the reaction is. So here I've underlined, it's the first order reaction. Why? Because if I have a 0 order, I'm going to use a different equation. If I have a second order, I'm going to use a different equation. So I need to have the right equation for what's going on. All right, so a certain first order reaction is 46% complete in 68 minutes at 25 degrees Celsius. What is the rate constant? Okay, so there's a couple of ways you can think about this kind of problem. This doesn't give us actual concentrations. So one way you can think about it is, let's just assume the first concentration was 1 and then go from there. The other way is to say, well, if I'm looking at a comparison between the two, I just need to know what the portion of it is. And I'll show you what that looks like in just a minute. But I've got this 0.540. Where did that come from? If I am 46% complete, I want to know how much I have left to do. So let's simplify. If I'm 50% done with the test, how much do I have left of the test? 50%. So it's just the difference between 100. So if I'm only 46% done, I still have 56% to go. So that's where that, 54% left to go. That's where that 0.54 comes from. Okay, and remember when I'm going between percents and decimals, I just move that decimal over by 2. Okay, so we pick an equation. Come on. There we go. Now we have 2 different equations. This is our first order equation here, but I also have this one. And the reason why I've written on the board the one that has the natural log with the 2 concentrations on top of each other is that we know about both of those. Okay, and we're looking for K. So I want to get K by itself as much as possible. So that's why I'm picking that equation. So I could plug in 1 for A0, and then 0.54 times 1 would be 0.54 for AT. I could do that. Or, oops, let me get the rest of the variables in here. I could say, okay, I have 54% left at time t, and I have 100% left at time 0. So I can do 54 over 100. Either way, I end up with 0.54. Now notice that I have, oops, wrong one. Notice that I have 54 over 100 in parentheses. That means I have to do that division before I take the natural log. So this isn't going to be natural log of 54, hit enter, and then divide by 100. It's going to be natural log of 0.54. I have to do the division first. Your calculator will probably open a parentheses with the natural log, so closing it off is going to be very helpful in making sure you get the right numbers. All right, so I plug in all of these things. And, okay, somebody plug that in. What do you get when you plug in natural log of 0.54 or natural log of 54 over 100? Negative 0.62 or negative 0.616 if you're looking at your calculator and you're like, wait, I got something a little different. So she just rounded it appropriately. Is that a reasonable concentration, negative 0.62? Because concentrations can't be negative. I can't say I have negative 1 mole per liter. There's no such thing, right? So if you get a negative number, either you messed up your calculation, or in this case, you're just not done yet. So going back to the beginning of the equation, and here, let me put this out here. Our natural log here is what we took. We need to undo that. Okay, so I'm sorry, I'm mixing things up in my head here. Okay, so we have a negative number, but we need to get K by itself. So we have 68 minutes, but we also have a negative in front of K. So we're going to divide by negative 68. So that negative 0.62 divided by negative 68, the negatives cancel. That's going to give us our positive number. So is 0.009, is that a reasonable concentration? Yeah, it's small, but it's a reasonable concentration. It's positive.
Why are the units,
Oh, good question. Because I asked the wrong question here. This isn't actually a concentration. We didn't solve for concentration. We solved for K. And K has units of per minute. So saying to the -1 is the same thing as saying slash minutes. Okay, which is weird if you're trying to think of what is an inverse minute. So try not to break your brain by doing that too much. But remember, our units for K are whatever we're going to have here. We'll cancel out units here to give us rate of molarity per minute. So we're looking at first order. This gives us molarity. This is molarity per minute. So K has to be per minute. That's where that comes from. Okay, second problem. A certain first order reaction. So again, we're dealing with one of these two equations. Has a rate constant of 0.0112. So which part of the equation is the 0.0112? Got lots of letters in here. Which of these letters is the 0.0112? Okay, that's our rate constant. Then it says the initial concentration is 0.69. So that's going to be this here. But the 0.69 is just the A0. It's not the natural log of A0. We still have to take natural log of it. And it says, what is the concentration after 13 minutes? So that's our T. So we're trying to find AT. So we want this as much by itself as possible. So I'm going to use the bottom equation. So we just talked about what those variables were. The A0 is the 0.69. K is the 0.0112 per minute. And we have 13 minutes have passed. All right. So take a minute on your calculator, see if you can figure out what this is. If you don't have your calculator, at least write out the equation with the numbers plugged in. All right, so as you plug that in, you should get something like this. If you did not get -0.517, make sure you took the natural log of the 0.69 and make sure that only the 0.69 was in there. So it may have opened a parentheses. If you didn't close that off, it may be trying to take the second half of that and also take the natural log. We're only trying to take the natural log of the 0.69. All right, so again, negative number. We're looking for concentration this time. I've got myself sorted out. Negative concentration, is that reasonable? No, so again, we're not done yet. So if we look at the beginning of the equation, we have solved for not the concentration, but the natural log of the concentration. So we have to undo it. And remember, the way we undo it is to use that E button. So E to the, so we're going to hit the E button and then type in -0.517. And when we do that, we should get 0.60. So is 0.60 a reasonable concentration? It's positive, right? So we can also think about if it's reasonable in terms of this problem. So we know it's a reactant. And we started at 0.69. So 0.60 is less than 0.69. Does that make sense? Yeah, some time has passed. We've done the reaction a bit. And it's not a lot less, right? We've had a couple of minutes pass, 13 minutes pass here. So it's not gone all the way down to 0. So it's still in the same ballpark. And that's reasonable too. All right, anybody still need this slide? Yes.
So, would we do 2 significant figures for the second to last step, or would we wait to limit our significant figures to the last step?
I usually wait to limit until the very last step. Technically, it kind of depends on where the parentheses are and whether you are adding and subtracting or multiplying and dividing, and natural logs have weird sig figs and all of that, but I usually wait until. Okay, so here's another question, follow-up question. So using the same information from before, now I'm asking, how long is it going to take the concentration to drop to 0.21? Now we're starting from the beginning of 0.69. Okay. So this time, since I'm looking for the amount of time, I'm going to use the rearranged equation, this one here, that has negative KT by itself. But I still have K is equal to 0.0112. I still have the initial concentration of 0.69, but this time my concentration at time T is 0.21. All right, anybody have an answer on that? I know we haven't had a lot of time here. Plug it in. What did you get? It is C. Now we can look at this and say A is less time, because remember before it was 13 minutes, less time than it took to drop just 0.09. So obviously A is wrong. B is more time, but it's not a lot more time. So I wouldn't expect it to be dropped that much in that amount of time. So C and D are the only really reasonable ones. All right, the last question, the one thing I want to point out about this is it doesn't say first order or second order or third order, but it does tell us what the rate law is. So from the rate law, rate is equal to KHI squared. What is the order of the reaction? Second order. And that means we're not going to use the natural log equations. We're going to use the 1/over equations. Okay, but obviously we don't have time to go into that. All right, so have a good weekend and keep a lookout for things posted on Canvas for you to do.